The presentation will be about anode-less solid-state lithium chemistry enables fast charging microbatteries with high energy density. Thank you very much, and the stage is yours.
Appreciate it. I appreciate everyone's time. So I'm going to be speaking about our technology, which we've been working on for the last 2.5 years at Ensurge. And as you see in the picture there, that's an inset of the stacked solid state microbattery. And to give a rough order of size, that would be about 8 mm by 8 mm in footprint, with a height of a few mm. Um, So, a quick word about the company. We are based in San Jose, California. We have been working on a thin film solid state microbattery over the last 2.5 years, taking that from initial development into commercialization. We have our own roll-to-roll facility here. We have made it quite clear that the way to achieve a cost scale and a path to commercialization is really to have a roll-to-roll product approach for these kinds of batteries. These are targeted at a quite a significant opportunity in the emerging class, emerged class rather, uh, of hearables, of wearables, of IoT devices. What we are not is an EV technology. So we are not interested and cannot use this technology for very large batteries. This is very much aimed at the microbattery space. By that we mean about 1 to 100 milliampere hour, and that's the sweet spot uh, of where this works. As I said, we are based in San Jose, California, and we have a full R&D as well as scale up line over here. So let's go first into the what the architecture of the battery is. This class of battery and technology, in terms of a thin film lithium-based cell, has been around for a while. The gap between capability and scale has really been about making the right choices to get to the right form factors. So as you saw earlier, we are uh, targeting applications where space is a primary constraint. Um, so by definition, we have to achieve adequate battery capacity, but in a very form factor restricted volume. So volumetric energy density is one very big key. The other part is flexibility in terms of the form factor. All spaces are not created equal, so we have to have a form factor freedom where we can change the height, the width, and the length depending on the application of the customer. So to get to high volumetric energy densities, since this is a thin film cell, the energy containing layers tend to be quite thin uh, uh, on the cathode, etc. So it's very important to get to high VEDs that we minimize the thickness of the substrate. A lot of the batteries in this class work on silicon substrates and other things, which can be, which can be hundreds of microns thick, which is a significantly higher number than the actual thickness of the cathode. So one thing we did upfront is we wanted to use our expertise in stainless steel based devices on roll to roll to use an ultra thin 10 micron thick stainless steel roll. Uh, so apart from providing a low thickness, which provides low overhead uh, into the battery, the other thing that the stainless steel provides is the ability to operate at high temperature processing. For this, you need other proprietary technology in the space to make sure the elements of the stainless steel and the battery don't mix. Uh, Expertise we had for a long time, but that getting the right crystal structure of the battery, being able to anneal at high temperatures, is very important to maximizing its energy uh, capacity. So those are two high level points for which we choose steel. Um, of course, there are quite a few others like its strength, its ability to act as a moisture barrier. But that's kind of more in depth. The other part for scale is to move from single wafer processing, which a lot of folks do, on for silicon-based or other devices, onto roll-to-roll. And so we have our own roll-to-roll facility with quite a range of tools, primarily in film-based, but we have both tools uh, for the existing as well as the next generation of batteries. The next part of the foundation is to have a manufacturable stack. A lot of the thin film solid state batteries with lithium use a pre deposited film of lithium on the anode. Of course, this makes it easier to have a lithium reserve to establish better cycling, etc. But this also makes it very hard to actually operate in production. So we made some pretty hard choices up front, which was to use an anode free chemistry, where the lithium is generated from the cathode on the first charge. This allows operation and packaging under much more manufacturing conditions. An example of this is we do not operate in a dry room, unlike most other battery companies. So we establish our process in a standard semiconductor clean room, which operates at a normal humidity. This allows personnel to be uh, in normal suits. And this was, among the core assumptions that we had to make, that in order to get the costs of manufacturing into reasonable shape, that we did not want to use expensive and hard to maintain environments. Uh, as you'll see in the next slides, in order to get the battery capacities and maintain small footprints, we stack the battery layers on top of each other, which means we have to package them using uh, some innovation, but which also uses elevated temperatures. If we have a pre-existing anode there of lithium, that makes those processes much less forgiving uh, to the environments. And that's the last part of the foundation, is that in order to maintain again the high volumetric energy density, apart from the substrate, which must be as thin as possible, we also have to have very thin overlayers of packaging, which must maintain a seal so that it does not allow moisture, etc., to start to come in. And so critical to have low substrate thickness and lower packaging thickness as these cells are stacked. And yeah, so an illustration on being able to maximize the energy density. On the left is the cell is the cell as made. You see a stainless steel substrate. The use of stainless steel has another advantage here, where we can use the stainless steel as the cathode, uh, as the CCC, the cathode uh, current collector. We do not need to put insulators around it and then put down expensive CCCs on top. This allows us to use a low-cost CCC that is compatible with the lithium-based cathodes. We use an electrolyte, of course, of lipon. We've been public about this, and as you'll see, no lithium that is pre-deposited. It goes straight onto the anode. It goes straight onto the anode current collector, and then the packaging um, stack above that. So this is one individual layer. These are now the lithium is now generated on the first charge, and it is maintained there so that the battery is not over discharged. We discharge it down to 3 volts or so, and so we always maintain a seed layer of lithium. The Another part of being able to get the high energy densities is to have N termination, so we don't waste space on contacts. A quick overview of the manufacturing process. We start with rolls. We have just one single patterning step. This allows us to use inventory across the board, and it's very important for manufacturing inventory optimization. This gets into test, where we test the good cells, stack the good cells, and then into encapsulation, metallization, packaging, and test. So now let's get into quick points about the data. So here's an example of a cell where we showed how quickly it can charge. So unlike lithium-ion cells, where the charging has to be slower or more careful to prevent formation of dendrites, etc., we do standard constant voltage charging at 4.2 volts. So this allows the battery to go to its full charge to go to its full charge straight away, and we hit over 80% of the capacity uh, in slightly over 20 minutes or so. Um, we do have to get into other areas for manufacturability because we are doing this roll to roll into high speed test. So every cell on the roll on the sheet has to be tested. So we do EIS test, extract the parameters, determine which cells are good for yield. So on the left is an example of an EIS curve of a single cell. On the right is of an activated and the discharging battery cell. So these cells operate at with since it has an anode of lithium uh, um, against the cathode. It goes. It has an output voltage of 3.9 volts. And here's some data about the package cell, about the cycling. We get very good CEs of over 99.9% when it's packaged. Um, as we all know, lithium essentially will react with anything, and so it's very important to have materials in the package that one will not react with the lithium itself, and two will also act as a moisture and oxygen seal so that you don't have a aerostatic loss. What we have not shown here is the unpackaged cells cycling. We have, of course, taken those also to hundreds of cycles, and it does not take a whole lot of moisture, uh, even inside a glove box to reduce the CE from 99.9 to 99.5. So it is very important that we have that the overall packaging is is in place and acts as a good encapsulant with good mechanical properties as well. Um, that's a quick data about the about our cell in this very quick talk. In summary, the key take-home points. What we have is a novel architecture which has been simplified and adapted to roll manufacturing on stainless steel to get to very high energy densities. Our targeted energy densities are in the range of about 700 watt hours a liter, which in the small form factor in the range, for example, in the range of about 10 to 16 milliampere hour or 50 milliampere hour is probably twice that what you would get from an equivalent lithium ion cell. As cells get smaller, lithium ion has a harder time maintaining a high VED because the overhead of the packaging starts essentially will dominate the amount of volume. We being inherently safe, non-flammable, can use more flexible packaging in a stacked format to get there, and that's our or advantage. As we said, we are relatively new entrants into the battery field, where we felt we had the technology and the scale to to make a difference in this market. We've made a lot of progress over the last 2.5 years, and are now engaging with significant numbers of partners and customers, and always open to the right alliances in that area. And again, to emphasize, we are not an EV battery. We are the first to be doing a high VED microbattery with solid state lithium and all its advantages in the 1 to 100 milliampere hour uh, capacity space. Uh, uh, Appreciate your time. Thanks for listening. I will open to questions now.
Thank you very much for the very interesting talk. We have already a lot of questions from the audience. The first question is from Yin Chao. He asked if do you think that additive manufacturing can play a key role in the microbattery fabrication?
Yes, absolutely. So, like we said, there are two parts in this. There's the fabrication of the core cell uh, of the battery, and then there's the packaging. And in both cases, both either present and the future, uh, we think that additive manufacturing can play quite a role in being able to achieve new form factors and energy densities, but only in the right step at the right time. We actually come from a long history of uh, uh, printed electronics, and so we are quite aware and use the right step at the right time, the right approach at the right step uh, uh, for printing.
Thank you. There is a question for slide 5 for the overlay top layer. Could you comment, please, why do you need this layer and why is the thickness changing?
Yes. So the overlay is essentially the packaging layers. Uh, the core cell by itself is a battery, but it is not a product. So that's just that's of course the heart of the whole product, the unit cells. We stack the unit cells on top of each other to make the battery what we need. So the overlay is really a combination of packaging layers that we use, which we have to keep very thin. And as when the you have the when you have uh, generation of lithium, you actually get a slight increase in the volume of the cell. And so it's important to have packaging also which can accommodate a, uh, certain amount of that volume change. So it's meant to illustrate it. It's not to scale.
Yeah, thank you. What limits the voltage window to 4.2 volts? Is it the cathode or the electrolyte?
It's really the cathode. We use LiCo. We've been open about that. And yes, you can charge up to, you can go and operate for limited times to get even higher energy densities, going up to 4.5 volts. But with excessive cycling in that regime, what will happen is that you take the crystal structure of the cathode at some point will start to collapse and you will lose a cycle life. There are
Mm,
other cathodes one can use for higher energy densities to operate at higher voltages, but these also come with higher impedances. The core factors that determine its use in product is basically the ability to discharge the battery at a high rate, especially in the pulse for communications. So we don't want the impedances to go high. We prefer to be going to 4.2 volts, maintaining the long cycle life, and
mm.
and still operating with very high energy densities in the small form factor.
Good. Two quick questions maybe before we
Yeah.
move on. What is the theoretical depth of the lithium layer after charging, and how do you deal with pressure variations?
Um, so typically, I cannot give you very in-depth answers on this as it's somewhat on the proprietary side. The rough depth under compression is of the order of small number of microns. Um, and it has pressure variations have to be dealt with the architecture of the battery. These are used in consumer electronics, so there's no way you can put external pressures on it. All of that must be accommodated inside the packaging architecture.
Thank you. And last questions, are you also considering other electrolytes?
So we are very focused on Lipon in this, and but we have adapted and are adapting that for production worthiness. Lipon is very stable against lithium, as you know. We would consider other electrolytes if they were very thin, very proven, very manufacturing friendly. But as everybody knows, any new material, especially the electrolyte, can take many years to prove and productize. And so that's our reason right now for sticking with Lipon.
Yeah, thank you. Thank you very much for the talk and the interesting discussion.
Thank you.
All the further questions, please meet the speaker in the speaker session.